Okay, welcome back, everybody. Let me check a couple of things here real quick. Okay. All right, so a couple of reminders. I just sent an email. I moved the midterm exam, I call it midterm exam for the lab. I moved it to Thursday instead of to Wednesday. Simply because, as I explained, I've not completed all the grading for the last lab, and I'll get that tonight. So it'll give you a little more time to look at your last lab before you do it. But I left it open, so if you want to take it on your regular time on Wednesday, it's open, so you're welcome to do that, okay? Or you can wait till Thursday. It basically is taking some of the questions from the previous labs and putting it into a midterm exam, and that's about it. Nothing complicated. Okay, so that's that part. Also, don't forget, today is exam number 2, chapters 4 through 6. If you have any questions, I'll be more than happy to bring them up and go over them right now. Or you can send it to me email. I stay close to my email, during exam days, as close as I can, so I can answer them quickly. All right, so at this point, any questions? Semester is going quick, we're getting there at the end here. So, hopefully you stay on top of things. I did add already a 0 onto the, let me explain this one more time, because I guess some people don't like the idea that I put a 0 in there. And let me explain why I do that. From previous experience, I've waited to the end. Now, first point number 1, the nomenclature exam is not due until the end of the semester. Yes, that's understood, okay? But it's been open since the beginning of the semester, and this is true for whether it be summer or any other semester. Now, you have an unlimited amount of attempts for that nomenclature exam. Now, you also have on the website, you have a resource, there's a link on the left side panel called StudyMate that will assist you with respect to this nomenclature, and I'm going to pull it up, and we're gonna go through it very quickly. Okay, so in the past, what I did is I waited to the end, before we put a grade in there. Okay, Eduardo is a little bit confused. Okay, well, we'll go over that. Not a problem. And I'm for those who are just showing up, I'm explaining about the nomenclature exam and why I put a 0 in there. Okay, because Canvas, first of all, Canvas does not incorporate your real grade until it's graded. Okay, so we have a multiple of assignments. You're doing good, but it doesn't include those assignments that haven't been graded. So in the past, what happened? 1 or 2 weeks before the semester ended, I had to actually put a grade in there. And if you had not completed that 80% level, I put a 0, resulting in those students that were in the borderline, it dropped your grade drastically. You probably saw what happened when I put the 0, your grade really dropped quickly. And I was to show you is that 10% could be a big factor, okay? Then before this, it would take, you had like 1 or 2 weeks to complete that assignment, and it became very challenging. I try to do it now sometime around midterm to show you where you truly are and what effect that grade does, okay? Yes, I fully understand it's not due to the 21st, but we also remember that on the 21st, Canvas shuts down and you don't have access after 11 p.m. to any assignments that you need to get into. So in this manner, by putting a 0 in there, now you know that what effect that 10% has to your grade. Yes, as everything gets graded, your grade will go up, okay, toward your true grade at the end. And if you leave that 10% alone, eventually you'll get a better idea where you truly are. And also, and with respect to, it could have an effect if you're in the middle of the grade scale. It could not have an effect, and that's not a problem. If you're happy with that, go with it. But if you're on the border, either border, it could jump you up to the next level or drop you down. Okay, so enough of that. Hopefully you understand why I do that, and that's for your purposes. I don't want to have you freak out at the end of the semester and really work hard and not be able to get that other 10% because you're on the board. Okay. All right. Now, the second point, to help you with the nomenclature, I have, as we progress through the chapters, been introducing the naming little by little. You do have a whole chapter of nomenclature. Okay. Now, this chapter, we're going to talk about chemical bonding, and I'm going to get more into naming these compounds. So that'll help you out with the nomenclature. Let's go to, they closed it. Let me load it back up. Okay. 1 second. My internet's been acting a little slow. All right. Okay, here we go. What I'm going to do is share with you the Canvas course. And it's just a reminder, I introduced this a while back, but I'm going to bring it in again to refresh your memory. On the far left here, let me go to the student view because that's, my view is a little bit different than from your view. All right, so on the far left here, the links, where the links are, you have a link called Study Mate. So if you click that, the following pops up, okay? This shows up, you just say continue to Study Mate, and you can click in here, don't show again, because it gives you, introduce you to Study Mate. You can actually utilize it for any other course, and you can put in some questions and so forth that would help you for other courses. So you have access to that. And down at the bottom, see Age of Discovery. That's a project that you are more than welcome to go in there and take a look at it. Give you an idea how to make a Study Mate work for you for any course that you want. Anyway, up on top, you see nomenclature. Click it. Now you have 2 choices. I recommend 1 or 2, either the flashcards or matching. You're more than welcome to utilize the other kind of games, if you will. I uploaded 140 some compounds, given the formula and given the name. And then what StudyMate does is uses these crossword puzzles or glossary or fill in the blank questions. And the reason I recommend just flashcards for matching is because StudyMate doesn't support like parentheses very well, and it's kind of confusing. So I would stick with the flashcard. So let's click the flashcard. So when you click that, what shows up is the following. This, of course, is a little bit foreign to you at this point, but it won't once we get to these chapters and then introduce it. But if you read it, it says lead. In parentheses, you have Roman number 4 and then hydroxide. Okay, so what you'll be given here is the name of a compound. That parentheses is a very specific piece of information. It deals with the charge on the metal, lead. So what we're dealing with here, and I'm going to go ahead and run through it very quickly just to introduce you to it, is the following. Let me change the color here. So when I read this, I see this Roman numeral. This Roman numeral belongs to the metal. And what that tells me is this, that lead, Pb, I gotta know the symbol, in ionic form, meaning that if we're talking about ionic compounds here, is in the +4 state, okay? If that was Roman numeral 3, it would be the +3. If it was Roman numeral 1, it would be a +1. In this case, it's a Roman numeral 4. Now, we use these Roman numerals for a some of the elements that do not have what we call an exact charge, oxidation number, okay? And my periodic table, which I'm going to show to you, shows you I talked about the sweet 16, meaning that these metals have a very exact, specific charge when they become ionic. That means that all the other metals can vary. So you have to be told which oxidation state that is, okay? The hydroxide from the periodic table, there's on the far left, there's what are called polyhydroxide atoms. And that just simply means that they come together in the packet. More specifically, they have a specific charge. This is what's called the hydroxide ion. The hydroxide ion, its formula is OH. And if you look at the periodic table on the left, you'll see these polyatomic ions, okay? And in there is things like sulfate, sulfite, and you'll find hydroxide. Its formula is OH, and it has a -1 charge, okay? Now, and we keep these as a unit. Now, when we put these together to write the formula, we have to write them such that the charges cancel each other out. So what that means that I have to put enough negatives here, because right now I only got 1, to cancel out the +4. So when I write it like this, it tells me I need 4 hydroxides to cancel out the +4, okay? Since this is a polyatomic ion, the way I do that now is I start writing P, but I use a parentheses, because the hydroxides I got to keep as a unit. I can't separate them, nor can I put subscripts. It is 1 unit. So if I need more than 1 unit, I put a parentheses. And now the subscript, that number 4 becomes the subscript for the formula. So that is the formula for lead 4 hydroxide. And to double check that, you tell it to flip the card. Okay, and there it is right there. There's the formula. Obviously, it doesn't support subscript, so you can see that number, but in your mind, that is a subscript, okay? All right, now that's using that. Let me clear this up. The other one is the matching, okay? And so if you click matching, what it does, it takes the formula, okay? And then it gives you a multiple of choices here, based on the formulas that were uploaded for you to select. And so your job here is to dissect the name right here and write the formula. Okay, so you can see you got lead and bromide. So what we're dealing, now here again, we got the Roman numeral, which tells you that we're working with the +2 ion. And the bromides are in group 7. When they become ions, they always have a -1 charge, okay? Because they're in group 7, they pick up 1 electron. And that's why we're going to talk about, I think somebody had a question about the valence shell based on the Roman numeral. So if you look at the bromide on the periodic table, you'll find it to be in group 7 as bromine. It needs 1 electron. So it has 7 valence electrons being in group 7, 7A. And so when it becomes ionic, it's a nonmetal, it wants to pick up an electron. Okay, remember nonmetals gain electrons, metals lose electrons. And so with that being said, we can see that the bromine will pick up 1 electron, and now we change the name to bromide because the IDE is an ion, okay? It is an ion. Now we got the 2 ions. We got the +2 and a bromide, and you can see to put them together to write the formula, I got to write enough cations. I have enough cations and enough anions. Or another way to say it, I got to have enough positives and enough negatives to cancel each other out. So when they come together, they have a 0 charge as a compound. So this tells me that I need 2 bromides for 1 lead 2 ion. So that 2 becomes the subscript. the formula now is PB Br subscript 2, okay? So obviously it's this one right here. Now, all the other ones you can eliminate because look, you've got nitrogen and oxygen, it has nothing to do with lead and bromide. You got bromide and fluoride, again, has nothing to do with the name you're given, so I'm going to eliminate that. I got iodide and bromide, nothing to do with lead, okay? Phosphorus and fluoride, nothing to do. So, you know, a lot of times the process of elimination, I can determine which one it is, and that's the long way to do it. The best way is to take that name and break it down into ions and then put it together in the formula, okay? All right, so those are the tools you have to help you with respect to naming compounds, okay? Now, the question was valence electrons on atoms in periods 4 through 7. Well, let's do this. Let's pull up my periodic table, okay? Now, if we look at, to assist you, now, when we determine the valence electrons, we can only do that with respect to the A metals, okay? So that's Roman numeral 1A, which is right here, the group 1A, all the way across to 8A, okay? So 1A tells you that there's one valence electron in that group, group 1A. Everybody in that group has one valence electron. Everybody in group 2A has two valence electrons. And as we go across, okay, getting confused because of electron configuration. Yeah, don't confuse the electron configuration with the valence electrons. So if we do the electron configuration for any of these elements, the outermost shell, the outermost energy level is what is considered the valence electrons, okay? And so let me do a quick example and we'll go over that. So going over to group 3A, which is right here, okay? Everybody here has 3 valence electrons, and group 4A has 4 valence electrons, 5 valence electrons for 5A, 6 valence electrons for 6A, 7 valence electrons. Notice the bromine there we had earlier. Okay, 7, and then the noble gases starting with neon have 8 valence electrons, but helium only has 2. Okay, that's its maximum for 2 valence electrons for helium. Its brew is the duet, if you will. Everybody else has the octet. Now the drive here is to attain the octet, obtain the outermost shell that is full, either with 8 or 2, and depending where it's at. Now, if we look at the, let me clear this up, the electron configuration of, let's just very quickly do carbon. Okay, carbon's in period 2, so what we got here is here. 1s2, 2s2, and then we go across to 2p2, okay, being the second. Now notice that carbon is in group 4, okay? So that tells me that has 4 valence electrons, which are represented in the second energy level. 2 of those 4 are in the s orbit, and the other 2 are in the p orbit, okay? So those are the valence electrons, not to be confused with the electron configuration, which is the whole description of where all the electrons and what orbitals and what energy levels they occupy. Okay? Does that kind of clarify a little bit for you? Kind of. Okay, so what part is it that we need to get you out of kinda to I got it? You can go ahead and unmute yourself. You can, if you want to tell us.
So I took the exam and they had a question on bromine.
Okay.
I think I'm getting confused on just the electron configuration, but I think I figured it out earlier because you were mentioning how when we go on period 4, D is actually on the 3rd level instead of the 4th level.
That's correct.
So I think that's where I was getting confused at the time.
Okay. Yeah, hopefully there shouldn't have been any questions to do electron configurations in the D.
It was asking for the number of valence electrons in bromine.
Okay. All right. It was simply asking for, and that's true for any element we can do. And so for any element, let's just very quickly, let's pick sulfur. Okay. So if this is sulfur, the question would be, well, you can have a multiple questions. They could say, all right, how many electrons does sulfur have? Okay, well, to answer that, you go look for the atomic number, it's number 16. That tells you it has 16 protons and 16 electrons when we're talking about the elements, okay? Now, of those 16 electrons that sulfur has, the question would be, well, how many are valence? So of those, what we do is we find its position, which is Roman numeral 6A. So that tells you that everybody in 6A has 6 valence electrons. So for sulfur, which has a total of 16 electrons, 6 of those 16 are on the outermost shell, which is specifically in the 3rd energy level, okay? Because it's positioned in the period that it's in. And so that would be in the 3rd energy level would be 3s2 and 3p goes across 1, 2, 3, and 4, 3p4. That is the valence shell for sulfur, okay? Now for oxygen, it also has 6 valence electrons, but it only has a total of 8. So of those 8, 6 of those 8 are in the outermost shell. Because it is in the 2nd energy level, the valence electron configuration, the valence electrons for oxygen will be simply 2s2, 2p. What did I say, 6? That should be, nobody caught that. 1, 2, 3, 4, p4. Okay, p4. So notice something here with respect to oxygen and sulfur. They both have 6 valence electrons, okay? Which for oxygen, those 6 are in the 2nd energy level, and those 6, 2 of them are in the s orbit, and 4 of them are in the p orbit, okay? And we know that because it's in the 4th column, starting from boron, from the left to right, 4th column. If we look at sulfur, which has 16 valence electrons, it's double the number of electrons that oxygen has. But of those 16 valence electrons, as in the case of oxygen, 6 of those 16 are in the valence shell, which means, based on this position, 2 of the 6 are in the 3s orbit, and the other 4 are in the 3p4 orbit, okay? Notice the configuration of the valence shell. S2, P4 for both cases, the difference being the energy level that they're in, because simply sulfur is a bigger one. And if we're going to do selenium, guess what? That would be 4s2, 4p4, okay? It also has 6 valence electrons, okay? But it has a total of 34 electrons because it's a bigger element. But because their commonality is 6 valence electrons, they happen to fall in place with respect to being in group 6A. And we can extrapolate that and work that with all the other nitrogen and phosphorus would be the same scenario. Even all the halides, bromine, chlorine, and fluorine, chlorine, and bromine, what they all have in common, and iodine, what they all have in common is there are 7 valence electrons. All of them have 7 valence electrons, okay? They happen to be in different energy levels. For fluorine, it is in the 2nd energy level. For iodine, it's in the 5th energy level because iodine just happens to be a bigger element, okay? But they all share the same number of valence electrons, and therefore sharing the same number of valence electrons, being in the same group, they all share the same reactivity. And being nonmetals, everybody here that I just highlighted in a rectangle will want to gain electrons, specifically 1, because they already have 7 valence electrons. All they need is 1 more. So everybody here, when they become ions, will have a net negative charge, okay? And if I go to group 6, everybody there will have a -2 charge because they have 6 valence electrons. They're striving for the magical 8. So they're going to pick up 2 electrons to fill that p orbit, okay? And then nitrogen and phosphorus, because I'm highlighting the major ones we work with, they have 5 valence electrons. And when they become ionic, they will gain 3 electrons. So they end up with a net -3 charge, okay? And those are the ions that they create. And the charge they create is dependent on which group that they're in and how many electrons they need to fulfill the valence shell to get it to that magical 8. On the other end of the spectrum, we have the group 1 and group 2A that are metals. And all metals want to lose electrons. So these guys are not gonna gain electrons because, first of all, you know, for beryllium to fulfill that magical 8, they already have 2 its valence electrons. There's 2 valence electrons for beryllium. That's going to take a lot of energy to pick up 6 electrons, okay? Pick up 6, very unstable, okay? So beryllium would rather just lose 2 than even attempt to pick up 6. And it just couldn't handle it because they would have 6 more electrons, but it's only got, you know, 4 protons. It'd be extremely unstable. All right, so then all of these would have a plus charge because they lost electrons. And by losing those valence electrons, now they become isoelectronic with the noble gas that's behind them. So lithium and beryllium, when they lose the electrons, okay, become isoelectronic with, guess who? Helium, the noble gas behind it. Sodium, magnesium, when they lose electrons, become isoelectronic with neon. That is the noble gas behind it. In contrast, the nonmetals like chlorine, by gaining 1 electron, becomes isoelectronic with argon. Fluorine becomes isoelectronic with neon. Bromine becomes isoelectronic with krypton by gaining 1 electron. And iodine becomes isoelectronic with xenon. Now, again, it becomes isoelectronic, iso meaning the same, electronic meaning the electrons, the same number of electrons as the noble gas in front of it or behind it, depending if it's a metal, okay? I did not say that bromine became krypton, okay? I didn't say that. I said bromine became isoelectronic with krypton. For bromine to be krypton, it has to pick up a proton. And that's a whole different story right there, okay? All right, so I'm hoping that maybe that made it a little bit clearer. And since we are here, okay, that's good. We are here at this periodic table, which brings me back to the Sweet 16, which we're going to use in this chapter here. All right. Now you notice I did that example with lead and had the Roman numeral. And I said, well, lead is one of those metals that, yes, they're going to lose electrons, but we just don't know. We cannot predict how many. It's variable because, for example, here in blue, we got copper, Cu. Well, copper, there's 3 types of copper, okay? There's copper, elemental copper. 100% copper has 0 charge, okay? It's the element. Now, copper being a metal will lose electrons, and it will lose either 1 or 2. Copper will lose 1 electron, and when you lose an electron, you pick up a positive charge, okay? I think of it in terms of humanity, humans. You lose negativity in your attitude, you become more positive. Maybe that will help, okay? All right, but it can lose 1, it can also lose 2. And so it could have a +2 charge. And I tend to put a circle around my charge, and you don't have to do that. That's just for me to tell me that's a charge, and that not to be confused with a subscript or anything of the sort. So I notice that it's a superscript. The charge is always a superscript. So what we have here are 3 forms of copper. We have the copper element that has all the electrons. That is 100% copper. We have 2 types of ionic copper. Ionic meaning that it lost an electron and becomes an ion. And it is copper 2 or copper 1. Now, it can be ambiguous because we can't predict which one it is. But when we put it together, you're always going to know the charge of either the cation or the charge of the anion, okay? Remember that. You're always going to know the charge of one or the other. And knowing that when you put them together, I have to put enough of each together, enough cations and enough anions so they have a net 0 charge, you can calculate what the charge is for the unknown, okay? And I'm going to explain the ones that you're going to know 100% of the time. And then some other ones down at the bottom is, remember the polyatomic ions I was talking about, the hydroxide? Well, now's the time to become familiar with it. Here's that table. These are by no means the full table that's out there in the world. This is just a little taste of some of them that we utilize here. And these polyatomic ions, the thing to remember about these guys is 2 things. One, they're units. They come together as a unit. We don't separate the if it's a nitrate, notice the name nitrate. We don't separate the nitrogen or the oxygen. They come together as N, oxygen, subscript 3, and overall has a -1 charge. If I need more than 1, this is where the parentheses come into play, okay? When I put a parentheses around it and then the subscript for whatever number I need that's more than 1. If I need only 1, no parentheses, okay? Only if I need more than 1. So these are some of the polyatomic ions. This one here, we're going to talk about a lot, the hydroxide. That is also known as a base. Next time you take Tums, that's what you're ingesting, a hydroxide, because that's going to neutralize the acid in your stomach. All right. Notice that the majority of the polyatomic ions are anions. We have very few cations, and only one is called the ammonium, which is a plus. Most everybody else is a negative, okay? So those are the polyatomic ions. The takeaway from that is that if I need more than 1, I put parentheses around them. Okay, now the sweet 16. For those metals that I put in highlighted in red, okay, these, when they become ionic, okay, when they lose an electron and become a positive charge, they will always have that respective charge. So everybody, all the metals in group 1, remember nitrogen is not a metal, hydrogen, excuse me, hydrogen in group 1 is not a metal. It's in that group because it also has 1 valence electron, right? Everybody else there has 1 valence electron. So the metals starting with lithium on down all have one valence electrons, they're metals, and so when they lose that valence electron, they always 100% of the time will have a +1 charge, okay? In group 2A, from beryllium on down, they will always have 100% of the time a +2 charge, okay? So right there, there's 12 elements, 12 metals that you know 100% of the time their charge. I'm calling it a charge, but down the road, we're going to talk about change the name charge to oxidation number. Okay, because right now we're dealing with ionic compounds. And when we get into covalent compounds, we're not really dealing with ionic compounds. So we will switch over to oxidation number. Right now, we'll call it charge. Okay, so those are the first 12. Now, on top of that, there are 4 more metals that will you'll always know its oxidation number. I circle that. Element number 13, which is aluminum, will always have a +3 charge, okay? Element number, that's aluminum right there, okay? Then we have zinc. Zinc will always have a +2 charge. And then we have silver, which is Ag. Silver always has a +1 charge, and then swing to the right a little bit. We have cadmium, always has a +2, and I circled the ion charges here in blue circle there. Okay, so now you have a total of 16 metals. 16 metals that you know, always will know 100%. They have an exact, remember we talked about exact numbers here? Here's another analogy. They have an exact charge, okay? An exact charge. And therefore, having an exact charge, when it comes to nomenclature, we don't use Roman numerals for these guys, okay? So we got sodium chloride, NaCl. We don't call it sodium Roman numeral 1 chloride, simply sodium chloride. Right? What does this mean? That means that everyone else, all of the other metals involved here, if whatever, they have a variable oxidation state or variable charge. And we don't know what it is unless we're told or we calculate it. Okay? All right. And those are for the cations that you know 100% of the charge. Notice down the polyatomic ions in that table. That's their charge. Look at nitrate. Nitrate, NO3 has a negative charge 100% of the time. Okay? They don't, that charge doesn't deviate. Then some sulfate has a -2 charge. Okay? So those anions, you know 100% of the time what their charge is. So if they're hooked up or combined with a variable charge like copper or any of the metals I've circled here, you'll be able to calculate what their charge is. Okay, and I'll explain that in a minute. Now, what about other anions? Let me clear it up. Group 7A, down from bromine, fluorine down to iodine. Always 100% of the time have a -1 charge. They're in group 7, they gain 1 electrons. Okay. Oxygen down to selenium. These 3, because those are the ones you'll see more often. Okay. They always have a -2 charge. Oxygen, when they're by themselves, not to be confused. Notice the name. Earlier I said this is chlorine, and when it becomes ionic, it becomes chloride. All of these, once they become a negative charge, an anion, their name gets changed to IDE. And that will give you a signal to tell you I'm dealing with a single element. Okay, I'll explain here in a second. Nitrogen and phosphorus, 100% of the time, -3 charge. So nitrogen, its name becomes nitride. Phosphorus becomes phosphide. oxygen goes to oxide, sulfur goes to sulfide, selenium goes to selenide, fluorine goes to fluoride, chlorine goes to chloride, bromine goes to bromide, and iodine goes to iodide. Okay, notice what all of these are circled. The suffix all gets changed to IDE. And so let's take a look so we don't get things confused. If we look at S for sulfur, that's what we call it, sulfur. Okay. Now, when it becomes the ion, it becomes sulfide. IDE, sulfide. Down here, we have the sulfate, SO4 -2, sulfate. Notice the ending 8. The ATE tells you I got oxygen involved with the whatever's the first part. In this case, it's sulfur. Okay. And then if it's got one less oxygen, and we have more detail on this, I got some other things when we get more into more, sulfite. When we get deeper into this, I'll explain how the oxygens work here. So we got the 8, the sulfite. So there's 4 types of prefixes with SUL for sulfur. Sulfur is the element. When it becomes sulfide, that tells you I'm dealing with the single sulfur element. That's it. It becomes ionic. I hear sulfate or read sulfate as a signal to tell you I'm dealing with sulfur, but attached to it is oxygens. How many? I look at my table. I got 4 oxygens and it's an ion with a -2 charge. I read or hear sulfite, ITE. Again, it's sulfur with oxygens. How many? Go to your table. Notice that the ITE ending tells you 2 things. It has oxygen involved with sulfur, but more than that, when I compare it to the 8, there's 1 less oxygen than there is in the 8. Notice the nitrate. Do the same exercise for nitrate and nitrite. Starting with nitrogen. That's the name. When it becomes ionic, it becomes nitride, right? And then it becomes nitrate, meaning there's nitrogen with oxygen, specifically 3 oxygens and a -1 charge. And when you hear or read nitrite, again, it's nitrogen with oxygen, but relative to the 8, there's 1 less oxygen. So NO3 -1. Okay. And so sometimes, as we're picking all these up, notice here that you have all these cations that I just showed you that are known. I'm beginning to give you all the anions. I've circled the nitrites, and guess what? I can start mixing and matching. I can hook up the lithium with the oxide, or the fluoride, or the bromide, or the nitride, or even hook up the lithium with any of these anions over here, nitrate, nitrite. And you're already starting to build up a database of chemicals, compounds that you can name, specifically ionic compounds, because these are all ionic compounds, which means it's a combination of a metal and a non-metal. All of these polyatomic ions down in the table are non-metals. They're units, but they're non-metals. Normally, we combine them with any metal up here. Okay. All right. So let me clear up this mess here. Any questions at this point? All right. Well, I need to close some windows because my bandwidth is slowing down on my end. All right. Any other questions? Kind of give you a preview of what we're going to be talking about here, but this gets us into chemical bonding here and how we're actually going to start putting things together. Specifically, we're going to focus first on ionic compounds, meaning metals and non-metals, and how we can put them together. Then from that, when we put them together, we're going to create a a generic formula, okay? And that from that generic formula, which is ABE in general terms, we go to the shapes table, and looking up the generic formula we created, we are able now to figure out the geometry of the compound we just made, okay? So you're gonna, if you haven't downloaded the shapes table, definitely are gonna need it. All right, so download the shapes table. Now, we talked about the goal. I've introduced that quite a bit with respect for elements to lose or gain electrons. The ultimate goal, the ultimate stability is to have that magical 8 valence electrons on the outermost shell. And that is achieved either by losing or gaining electrons. The thing to remember about that is we go from an element, which is neutral charge, to now we have an ion, which is either a cation or an anion. And depending what happens, it will lose all metals, as I stated. It's etched in stone, okay? Etched in stone, all metals. And that's why it's important, if you look, remember that table I gave you where the table designated who are the metals and who are the non-metals and who are the metalloids, okay? That stair step tells you anything to the left of the stair step, to the left are metals. So that means that they're gonna lose electrons, okay? How many depends on what metal it is. On the right side of the periodic table, on the stair step, I should say, we have the non-metals, and they strive to gain electrons because they're closer to fulfilling and filling the outermost shell, the valence shell, to get to that magical 8. Okay. So when we combine a metal with a non-metal, a metal, ionic metal, and a ionic non-metal, we have a ionic compound, which forms an ionic bond. Now, the thing about these ionic bonds, we're going to learn with the next type of compounds that there's a sharing of electrons, but that's not the case with ionic bonds. Ionic bonds, they have an attraction to each other. Why? Because I got a full-fledged negative and a full-fledged positive charge. Negative and positive attract to each other. So they come like two magnets, if you will. Think of them as two magnets. We call that electrostatic charge, attraction. They come together. And they form what's called an ionic bond. There's no sharing of these electrons. The anion and the cation have a full-fledged charge. Okay? The other aspect about ionic compounds is that all of them, when placed in an aqueous solution, aqueous meaning a water solution, they will break apart. So, you know, if I can, I'm trying to think of an analogy here. I know I got this my little nebulizer here with a cap. Okay, electrostatic charge, they attract to each other. It's not a permanent attract to each other. Okay, electrostatic charge. I got an anion and a cation that come together because of their partners. Now, when I put this in an aqueous solution, the tendency for ionic compounds is to do this. They separate. They do what is called dissociation. They dissociate. They dissolve in the aqueous solution. Now, some ionic compounds dissolve 100% and completely. Some do not. They may be a small percentage, and they call it insoluble. But even when an ionic compound is classified as insoluble, there's always a small percentage of these ions in solution. And now we're going to learn about that too. That's called solubility. We're going to learn about the solubility rules, you know, and you might say, where did I learn that? Well, I'll tell you, I'm glad you asked. Periodic table, far right corner, solubility rules. Very simple table that tells you, okay, if I look at the ionic compound, can I determine whether it's soluble in water or not? Insoluble. But the point is this, even though it's classified as insoluble, there's a small percentage of it still breaking apart. It becomes ionic. It would still conduct electricity because it's ionic. All right. Now, when we start putting these ions together, the thing to remember is, opposites attract. So we're not going to combine two positive metals with each other. It's going to be a combination of a metal and a non-metal, negative and a positive charge. So in this case, we got calcium, and obviously the bromide will be a better partner than the lithium, because the lithium being positive will not be attracted by the calcium ion. So some examples of ionic compounds is this. We got calcium, for example, chloride, very similar to sodium chloride. Notice I started to give you names here. Okay, so what I do is I have KCl, okay? The fact that I have combined a non-metal, you got a metal here and an NM non-metal combined. That tells me I have an ionic compound. So that means that I need to figure out, what I do is I break it down to the ions. So I know the chlorine is in group 7. So when it becomes ionic, it will have a -1 charge. So now I write the chloride as a negative Cl with a -1 charge, okay? Because it is combined together with potassium. The name for the metal does not change. It's potassium, be it in bonded or as an element, it's still potassium. It's just to distinguish, it's either going to be the potassium atom or the potassium ion. That's it. But with chloride, automatically, if you see the name written chloride, IDE, you're not thinking chlorine, you're thinking ionic chloride, okay? And so being potassium is in group 1, right? So that tells me that in ionic form, it has a +1 charge. So here in this example, I simply can put potassium ion plus with the chloride, a 1-to-1. I got 1 potassium, 1 plus, 1 negative. I combined it, and that is the formula, KCl, for potassium, and then the name will be chloride. Okay? We do the same here. We got the next one, Ca, yeah. All right, here how it works like 99% of the time. This is like a binary compound, potassium chloride. In other words, there's two elements there. There's not one element that's central. It's just they're together. They're linear. There's no one that's better than the other, so to speak. Okay. When we start adding more, generally what happens is the first element you see is the central element. There's always going to be a central element, and then what's bonded around it is whatever's afterwards. So what we have here is calcium with a +2 charge, and then around it will be the 2 bromides. Okay, attracted to the charge. Okay, and so what we do is we need 2 bromides, so we put a subscript. So now we have CaBr subscript 2. Okay, that's what it's telling you, that calcium is the central atom, and then around it, attracted to the calcium +2 in the central, are the 2 bromides. Okay, its name will be calcium bromide. Straightforward calcium. And notice we use bromide here, but you can replace the bromide with the chloride or the iodide or even the fluoride. So you see how you're starting to build up a database of different chemicals. We use calcium here, but you're more than welcome to use magnesium, or even sodium or lithium, any of the other metals, or even the ones that have a variable oxidation state. Well, we're going to get to that in a second. So, you know, by the end of this chapter, you should have access to, I don't know, 600-700 different compounds that you can mix and match and put together and even be able to name them. All right. So these are examples of ionic compounds. Let me clear this up a little bit. Okay. Now, with respect to nonmetals, these are when they bonded to each other, we have a covalent compound. Okay. Ionic compounds, metal, nonmetal, covalent compounds, and look at the term covalent, meaning meaning that they're going to kind of share, coexist, if you will, the valent electrons, the valence electrons, hence the word valent. So they're going to share the valent electrons and they're going to form an actual bond. Whereas ionic compounds are like this, attracting to each other. Covalent compounds are taking electrons and actually doing an overlap and actually making some type of a bond, okay? Now, one of the big differences with these two is when we put the covalent compounds in water, like I talked earlier about the ionic compounds, they do not dissociate. They stay intact, okay? With the exception of one type, and we'll get to that, and those are acids, okay? All right, now some examples of covalent compounds obviously is water, H2O, CO2, that's carbon dioxide, you know, all of the diatomic elements. Everybody there is non-metal, excuse me. You don't see any metal involved here. All right, so why is the formula CaBr2? Okay, why do we have 1 calcium per 2 bromide? I kind of touched base on that a little bit earlier, is that, well, what we have to do is when we're given this formula right here, recognize that we have calcium, which is a nonmetal, and bromide, okay? Now, not to be confused with this, you know, people will say, well, how come that's not bromine versus Br2, okay? Now, notice here, the second bromine together, there's nothing else bonded. The way it's written, there's just 2 bromines together, okay? That is the element, the diatomic bromine. This is not the same as seeing a metal first, followed by 2 bromides that follow it, okay? If you don't see the calcium, then you have this situation. But if you see a metal here, and I just put calcium, but it could be any metal, followed by the bromide, it is an ionic compound. Note the difference there, okay? So, and once we figure out that calcium, you know, write it into ionic form, okay? So we know that calcium is in group 2. So calcium will always have a +2 charge. It's one of the sweet 16, okay? And Br, which is the bromide, it's in group 7, will always have a -1 charge in group 7. Becomes ionic, it has a -1 charge. And when we put these together, I got to have enough negatives to balance out the positives. So I need 2 bromides for every calcium +2. So this 2 that I wrote here in front of the bromide becomes the subscript in the formula. Okay. Let's do, for example, aluminum. Aluminum is aluminum chloride. We know that aluminum is a group 3 metal, and it's part of the sweet 16. Remember the list I gave you? It always has a +3 charge. Okay. So here this is, they're asking you to write the formula for aluminum chloride. All right, well, before I do any of that, I gotta put them into ionic form first. So aluminum, ionic aluminum has a +3. I know that the chloride, like the bromide, is a group 7 element. And when it becomes ionic, we'll have a -1 charge, okay? Now, I need 3 negatives to balance out the +3 of aluminum. Therefore, I put a 3 there in front of the Cl-1 to tell me that when I need 3 chlorides. So therefore, when I write the formula, Al, I write it without the charges. I bring them together, and that 3 becomes the subscript. So that is the formula for aluminum chloride, okay? Now I need to start to learn to work in both directions. I'm given the name, figure out the formula. I'm given the formula, write the name. And that's why I did a double arrow here. And that's basically nomenclature. So you can give them one or the other. Now notice I didn't put Roman numeral 3 here. Why? Because aluminum is part of the sweet 16. It has an exact charge 100% of the time. That's known by all the scientists in the world. So we know that we don't have to put the Roman numeral in there. And so does the scientists in the other end of the world, okay? There's an organization called, the acronym is Iupac. It's an international nomenclature organization that sits down and figure out the names for all the compounds. There's certain rules. So the purpose of that is to not create any ambiguity. Because earlier I explained that there was the name of 2 types of copper, copper 1 and copper +2, right? Well, in the olden days, so to speak, they were using the term cupric and cuprous, and it was very ambiguous, and people got confused big time. So to eliminate that, it was decided that if it doesn't have an exact oxidation state or charge, then we utilize Roman numerals to determine what oxidation charge or charge it is, okay? Therefore, to eliminate any ambiguity in naming compounds. All right, that explains why there's 2 of them. Now, this exercise here is the question is, which compounds are ionic? Well, you got to remember, to answer this question, we have to determine what do we mean by an ionic compound, and that is a combination of a metal / non-metal, okay? So that means that you have to be familiar with who are the metals and who are the non-metals, okay? So if you look at K, potassium, a metal, Br, which you be tempted to say bromine, okay? But remember, it is bonded here with potassium, which should tell you it's no longer bromine, it's bromide, okay? So definitely, I got a metal and a non-metal because the bromide is a non-metal. So that's ionic, okay? We got sulfur and oxygen. Well, if we look at their position in our periodic table, they are to the right of the stair step of the periodic table. Therefore, both sulfur and oxygen are non-metals. Therefore, they are not ionic, okay? Looking at hydrogen and chloride. Well, it's hydrogen, even though it's on the far left, group 1. I remember I told you that even though it's in group 1, it's not a metal, it's a non-metal. And we got the chloride, which is also a non-metal. So definitely that's not ionic, okay? Which brings me to, if you notice in the nomenclature, if you've been taking the quiz, you know, there's 2 types. There's HCl, which is normally a gas, and then there's HCl, which is in your stomach and denoted as aqueous, okay? It's an aqueous system. Now, when it's an aqueous system, we have hydrochloric acid because it becomes acidic in nature, okay? When it's not an aqueous solution, it's just hydrogen chloride. with the name. Now, what I've been doing is giving credit if you name one or the other in the nomenclature, but I just want you to be aware why Canvas, if you write down hydrochloric acid, it counts it wrong. It's because it's thinking in that example that is in the gas state should be called hydrogen chloride. But I check it and I give you credit for either one of those, okay? All right, now the next one is BR2. Notice 2 BRs, that means no metal in front of it, so definitely I have a ionic, specifically a diatomic compound, okay? The element bromine. And then carbon and oxygen, carbon dioxide, 2 nonmetals, definitely not ionic. And then at the end, we have magnesium and the chloride. Like potassium bromide, definitely ionic. So of these examples, only 2 of them are ionic. Everybody else is ionic. Let me back it up for a second, and let's do the name real quick, okay, of these compounds. Some of these you may be familiar with, some you may not. That's okay. All right, so this one here, we see potassium, so it's potassium, okay, and then bonded with it is the bromine, but since only 1 bromine here and is bonded to potassium, it is bromide, it's ionic. So not bromine, but bromide, okay? All right. The non-ionic compounds, specifically the covalent compound. Well, the first, notice we got the first element. That is like 99% of the time, that is the central atom. So you see sulfur. And so its name remains the same, sulfur. Okay? Now, whatever is bonded, whatever non-metal is bonded to the central atom, the "ide" nomenclature continues, whether it's ionic or covalent. So here we got sulfur, which is the central atom, and then 3 oxygens bonded around it. We're going to learn how things like that are bonded here in a bit. But the name remains as oxide. Okay, but we got to take it one step further. Since it's not ionic, it is covalent, and only covalent compounds use prefixes. In this case, there's 3 oxygens, so the prefix is trioxide, okay? Trioxide, so we got sulfur trioxide. This one here, I explained it's the hydrogen chloride. Okay, and then we got bromine for BR2, bromine, it's the element. This one you're familiar with. Notice that we got carbon. We don't change the name, still carbon. So carbon is the central atom, and then bonded to carbon are 2 oxygens, which the name is oxide. And since it's covalent, meaning 2 nonmetals, we got to use prefixes, and there are 2 oxygens, so guess what? Hence the di, carbon dioxide, okay? And then we got magnesium. All right. Notice that we did not say trichloride or dichloride, just straightforward magnesium chloride. So when it comes to prefixes, okay, to prefixes, there's no prefixes for ionic compounds. There are prefixes for covalent compounds, and we'll have more on that down the road here in a bit. All right. Okay, ionic bonds. All right, so we had the nitrogen atom, Okay, notice this nitrogen atom. And then we have the chlorine atom. Okay. And they have a diameter. Now, if you recall, one of the questions I asked earlier, I said, all right, extrapolate the information, meaning if I were to lose a valence electron, what happens to the new radius? And we agree, which is correct, that for a metal, losing an electron, when it lost an electron, the next valence shell is the next one in. So the overall radius is smaller. And if you notice that here's sodium atom of an X amount of radius. When it becomes the ion, notice its relative size now. It lost its one valence electron. And so the next shell in is the one that's full. So its diameter decreases. The chloride atom has a small size as to the far right of the periodic table, okay? And when it becomes ionic, it picks up one electron. And its size gets bigger. Its diameter gets bigger. Why? Because now it has an extra electron. It has 7 in its valence shell. And now it's picking up one more. Now it's got that happy 8. Well, you know, negatives repel each other. And so what happens to the overall radius of the ion is it gets bigger, okay? And it's denoted there by the color. Notice how it got bigger when it becomes the ion. Now, they each have a full-fledged positive and a full-fledged negative. And so they have this attraction to each other, an electrostatic attraction, simply because the attraction is a positive and a negative. And so you can see that they're just sitting there attracted to each other. And this will represent sodium chloride, good old-fashioned table salt, as we call it, but sodium chloride combined. And you can see the small sodium ions next to the chloride ions. And it's a big giant matrix, you know, all very organized and so forth. Okay, now, if this were to be placed in water, dump this in water, that matrix gets broken apart and it's all separated. Specifically, sodium chloride we know is very soluble in water and would dissolve 100%, totally break up that matrix. Okay, so notice that the size, the radius change. All right, so let's talk about, we talked briefly about this earlier, and we're going to rehash it because this is how we grasp how we are putting elements together to create compounds, okay? You know, we're at the state we learned about the elements, that's the letter of our alphabet. Now we're taking the letter of alphabet to create words, in this case, compounds, okay? So let's consider magnesium and sulfur. We know that magnesium, atomic number's 12, okay? So it has 12 protons and 12 electrons, so the net charge is 0, okay? Because I got 12 positives and 12 negatives. Net charge is 0. They cancel each other out. It's a group 2 metal, okay? Plus being a group 2 has 2 valence electrons, and it's a metal, meaning it would lose 2 electrons. So now it has 12 protons. That has not changed, okay? It's still magnesium. But it did lose 2 electrons. Now it has a total of 10 electrons, and it shrunk in size and diameter. So its net charge now is a +2. And so we put in superscript +2. Whether I put +2 or 2+ makes no difference. How was asked that? Makes no difference. This is what I mean. +2 versus a 2+. No difference whatsoever. It's still a +2. All right. If we take a look at the sulfur atom, it has 16 protons, 16 electrons, it has a net charge of 0. Okay. Sulfur is a nonmetal. Being a nonmetal, it's in group 6, it will pick up 2 electrons. So now it still has 16 protons, but now it has 18 protons, and it has a negative charge of a -2, a net charge of a -2. And so the ions formed are the +2 and the -2. Now we can put them together to write a formula when they come together, okay? And since there's a +2 and a -2, they come together on a 1-to-1 ratio. So the formula for magnesium sulfate is simply MgS, okay? It's a terrible looking S there, but you get the gist of it, right? MgS, okay? And that is magnesium. Note the name change, went from sulfur to sulfide. And so we got magnesium sulfide. The IDE again is telling you I got sulfur up front, that's S, but the IDE at the end tells you I'm dealing with the single element and it's the ionic form of that single element. Okay, like nitride would be nitrogen with -1. Chloride would be Cl with a -1. Okay. All right. Got a question here. Yeah, 99%, 99.9% of the time, metals are written first, and the name will always goes first. Okay. The question was, do metals go first all the time? That'll be yes. Even for the covalent compounds, generally the first element written is the central atom, and then whatever follows, like carbon dioxide. Okay. You know, this means that carbon, and you're always going to be told who the central atom is, and you're going to be told by, it will be underlined or its symbol being bold, and that tells you that whatever follows is bonded to the central atom. Something like carbon monoxide, you know, it's linear. There's no central atom. Either the carbon or the oxygen can be the central atom. There are just two things together, two elements put together. But when you got more than one, you're always going to be told who the central atom is. Okay. All right. Now, recap on ionic signs: that cations lose electrons, okay? And so by losing electrons, two things happen. The valence shell is now empty. The next valence shell is the one in that's full. There's more protons than there are electrons. So obviously, it just makes more sense that the whole thing gets shrunk down even smaller. As compared to anions, they pick up electrons. They got a negative charge. They come in and the place is crowded already. I add more electrons, it gets even more crowded, more repulsion. The size goes up. Okay. So with that being said, questions as follows could be answered. It's either true or false regarding an ionic bond between aluminum and iodine. Okay. And so it might even help to write the ions in this question to help you kind of keep track of what's going on. We're going to combine aluminum and iodine. Well, if it's ionic, aluminum is in group 3, so aluminum ion will have a +3 charge. Okay. Iodine is in group 7. When it becomes ionic, becomes iodide. Okay. Just like the chloride and the bromide, and it ends up with a -1 charge. So it's picking up electrons. And that means if I were going to put these together to form a compound, I would need 3 iodines to 1 aluminum ion. So it'd be A iodine, I3. Okay? Excuse me 1 second. Tell you what, let's take a break. My little one here is asking for something. Let's come back in 15 minutes. I have 2:21. Let's come back in 2:35. Okay. All right, I'll be back. All right, sorry, little technical problem. Anyway, let me continue here. The questions here are basically true or false. I'm asking you regarding an ionic bond between the aluminum and iodine. Okay, so being an ionic bond, I created the ions that would be made and the formula. So aluminum is a group 3, will have a +3 charge, and iodine, which becomes iodide, is in group 7, has a -1 charge. So the formula will be Ali3. Now I'm set. I have an ionic compound, and we can start answering some questions. It says here the aluminum atom loses electrons, and the iodine atom gains electrons. And of course, that would be a true statement, right? Because aluminum is a metal and the iodine is a non-metal. So that would be true. Okay. Give this some thought. The aluminum atom is larger in radius than the aluminum ion. Would that be true or false? What do you guys think? Okay. Basically, who's bigger, the atom or the ion? Okay. I got one true. Right? Think about this. That is true. True statement. Now, bear in mind, these questions could be reversed, so they could be asked in a different way. All right. The iodine atom is smaller in radius than the iodide ion. And that also is a true statement because it gained electrons, okay? And so the iodide atom would be greater, have a larger radius. And then the answer, the question here, I should say, is the aluminum and the iodide ions form a bond by attraction. And that, again, is a true statement because remember, ionic bonds come together because the metal and the non-metal have a full negative and a full positive charge, and they're attracted to each other. Excuse me, I'm going to sneeze here. True statement. It's electrostatic attraction. Not to be confused with covalent bonds that actually have a sharing of electrons. Okay, with respect to, not much to say about metals, other than to say that pure metals are just, metals in general are just a sea of electrons all around them, and little areas of positive charges. So basically, these electrons are going from where they're at to these positive charges. A lot of times they kick another electron off, and it's like dominoes, And the point being that if we think about it, the electrons are generated in some like Palo Verde, where they have the nuclear reactor generating electricity. That electron that's generated over there is not the same electron that you get as you plug in your hair dryer. As it travels down the wires, it's just kicking one electron out and just moving that until it comes to the wire. The electrons on your wiring system that then eventually go into your hair dryer, whatever thing you are generating electricity. So, all right, so, okay, let's briefly talk about covalent bonding. As we talked about ionic bonding, where there is a electrostatic attraction. With covalent bonding, these, first of all, they're nonmetals, and when they combine and share the valence electrons, okay? They share the valence electrons. Now, the key point about this is this. The sharing part could be either equal sharing or non-equal sharing. And we'll have a lot more to say about that. But if you remember that back when we were talking about the EN, electronegativity, I stated that that aspect is important to determine who is sharing their electrons more than they're shared, but one of the elements is pulling the electrons onto itself with a greater force than the other one because it has a higher electronegativity, okay? Resulting in a polar bond. So we have covalent bonds where they're sharing, electrons are being shared, and you have either equal sharing, which create what we call non-polar bonds, because there's equal sharing and there's no kind of a charge one way or the other. And then we have unequal sharing, where the electron density is pulled on to one of the elements with a greater strength, resulting in a polar bond. That aspect results in different chemical properties, okay? Now, there's three types of bonds. There is a single bond, a triple bond, a double bond, and a triple bond. We designate that with lines. For example, if I have a bond between A and A, I can draw A at one line. I'm just going to call that B. So I got two elements here, two nonmetals bonded with a single bond. That single bond has two electrons that are being shared between A and B. You can also have a double bond, which is designated by two lines, okay? Now, again, every line here represents two electrons. So if I have a double bond, then I have a total of 4 electrons that are being shared between A and B. We haven't talked about sharing equally or not equally. Right now, they're just being shared. And we can also have a triple bond. So we have 3 lines where we have in here a total of 6 electrons. Now, the point here that every line represents 2 electrons. And when we start putting writing formulas, keep in mind that there must be 8 electrons around all the elements, all of the atoms that are involved in this chemical bond, okay? And if it's being shared, okay, then that 2 electrons for the single bond are being shared by both A and B, and therefore they can count as part of the octet for either A or B. For example, we can have an example where we have a single bond between A and B, and then I'm going to, by dots, I'm going to designate each dot represents an electron, okay? Keeping in mind that that line has 2 electrons. So if I pick a dotted line here, to the left, there are 8 electrons around A, okay, total of 8. There's a total of 6 that are not shared with A, okay? But that one that is shared counts to both A and B. So there is a total of 8 electrons around A, and therefore the octet, the magical 8 octet rule has been fulfilled, okay? If we look at B, the same thing is true. It has 6 electrons. Each dot represents an electron. I can either designate it as a line or as 2 dots. Okay, here's the other thing. I can go either make 2 dots or I can draw a line. Both are the same thing and both represent the same thing. It's much easier to just draw a line than to deal with 2 dots all the time. You might end up losing dots. So I can write it either like that, or I can do it like this, where I can draw a line that represents 2 electrons like that. Both are the same. Both of these are the same, the left and the right. The point of all this is this. A has 8 electrons around it. 6 of them are not shared. 2 of them are shared. And the same is true for B. B has a total of 8 electrons around it. There are 6 that are not shared, and there are 2 that are shared with A, okay? So the octet, the 8 electrons in both cases has been fulfilled, and this is a stable configuration. The only exception to this is hydrogen. Hydrogen will always only have 2 electrons. Okay, so you'll always see only 1 bond with hydrogen. You won't ever see 2 bonds with hydrogen or even 3 bonds with hydrogen. Okay. All right. So we have examples of carbon dioxide, which we designate here with space-filled models here. But we're going to learn this. We're going to learn that, for example, carbon dioxide is written shorthand CO2, okay? But if we wanted to write the formula, we're going to learn that this is the formula for carbon dioxide, okay? Carbon dioxide has, around the carbon first, you can see, remember, there's 2 double bonds on the left, 2 double bonds on the right. Around carbon, there's a total of 8 electrons. 4 of them are being shared with the oxygen on the right, 4 of them being shared with the oxygen on the left as double bonds, okay? And if we look at the oxygens, the one on the right has 8 electrons around it. 4 of them are being on the oxygen itself, designated by the line, or it could have been 2 dots. And 4 of them are shared with the carbon. So the octet is fulfilled for the oxygen on the right. And we can do the same thing with the oxygen on the left. There's a total of 8 electrons around it, and the octet again is fulfilled. So this is the general structure for carbon dioxide. And because of the way it's put together, results in certain properties that we're going to learn about, okay? Now, if we look at water, which we're gonna learn about its structure, we will find that the oxygen has a total of 8 electrons around it, of which 4 of them are on the oxygen itself and not shared. And the other 4 are shared with the hydrogens, okay? The hydrogen doesn't have the octet rule, has a duet, okay? Put that in long-term memory. So therefore, that bond, there's only 2 electrons. So for hydrogen, its duet has been fulfilled, okay? It only has room for a total of 2 electrons. So it's happy, both the right hydrogen and the left hydrogen. And the oxygen, again, is also stable because the duet is fulfilled for the hydrogen on the left. Now, I want you to remember something else. These 4 electrons on the oxygen, okay, there's 4 electrons, they're all repelling each other, okay? They're repelling each other, and because of that, what results is this bond angle, which we have means to measure this bond angle using spectroscopic methods, but this bond angle is not what we think it is. In fact, it gets shrunk, okay? It gets pushed in because these we call these lone pair of electrons, these 4 electrons have negative charge and they repel each other, so they tend to take up more space. But there's a limited amount of space around the oxygen. The result is that bond angle between the oxygen and hydrogen gets crushed in, okay? All right, something to remember. And again, with that occurring, again, has an effect on the property of the chemical itself. Okay, this is a rehash of single bonds, double bonds, and triple bonds, okay? Single bonds are 2 electrons, okay? It could be either shared or it could be a pair of electrons on an element. And then we got 4 double bonds. A double bond, because it's the 4 electrons is what I meant to say, and a triple bond, 6 electrons, okay? Single bonds are generally longer and generally the weakest. So if I were to draw a single bond with respect to 2 carbons bonded to each other, it's a single bond. And I want to compare it to a triple bond, which is between 2 carbons, okay? That bond length in the triple bond is kind of shrunk in much more than the single bond. Okay, so single bonds tend to be weaker and longer compared to triple bonds, which are shorter and stronger. In fact, triple bonds have a lot of energy associated with it. You're familiar with, you know, if you did some cookout this past weekend, you use propane tank, okay? It's hot enough to cook your food, okay? Has a sufficient amount of energy. Or if you're lighting your flicker bit, your lighter, that's butane. Those have single bonds. But there's such a thing as an acetylene torch. Acetylene is a triple bond hydrocarbon mixed with oxygen, a lot of heat given off, hot enough that you can cut metal with it. So there's a lot of energy in that triple bond compared to a single bond. All right. Now, when we looked at covalent bonds, okay, what was thought was the following: is if the hydrogen atom, which has a radius and it has the units of nanometers, okay, very small, we're down at the atomic scale. You know, I'm sure you've heard of nanobots, right? Down at the atomic scale, 10 to the negative 9 meters. So we have a hydrogen atom, radius approximately 0.037 nanometers. And if you look at the chlorine atom, okay, its radius is 0.099 nanometers, okay? When the hydrogen, this is hydrogen, and then the chloride combine to create hydrogen chloride, okay? It was thought that the bond length between the hydrogen and the chloride in the molecule would be the sum of each individual radius, okay? Thinking that it would be, the total would be, you know, 0.136 nanometers. Well, on measuring this and getting the calculations done, it was determined that the actual bond length between the hydrogen and the chloride in hydrogen chloride was actually 0.127 nanometers, which was much less than the combined radius of each individual atom. So that the thought was, what's going on here? Well, what's happening is this, okay? Is when they combine to create a covalent bond, that in this sharing, unlike the electrostatic attraction where there you have the positive and negative just coming together and just you know, doing this, the chemical bond, there was some actual overlap between the electrons. And in fact, that's what's going on. If you look at this area here, there is some overlap between the hydrogen atom coming in. Now keep this in mind. If we look at the atom itself, we have the hydrogen with one dot, one valence electron. If we look at chlorine, okay, it's in group 7, and guess what? It has 7 valence electrons. So each dot represents the valence shell, right? Well, when they combine together, one electron from the hydrogen atom and that one electron by itself from the chlorine atom come together to create this bond where they share 2 electrons to form HCl. And there's an overlap, and that I colored that area in, and it's an overlap, which explains why the overall bond length between hydrogen and chlorine is 0.127 nanometers and not the expected sum of each individual radius. And that is because covalent bonds overlap, okay, when they're sharing electrons. And they overlap even more when that sharing is unequal. Okay. All right, with respect to energy and bond formation, to break or form any bond, energy is required, okay? So breaking a bond, we want to break a bond, break it apart, okay, that always requires energy. And so when we write a reaction to demonstrate what's happening, energy is in the reactant side of the arrow, okay? And that tells us that that energy is absorbed by the reactants. And being absorbed actually gets cold, okay? And we call that endothermic process. It's an endothermic reaction, okay? So here we're writing, we've got hydrogen chloride, it's a gas. If we put energy into the system, it's a reactant, so it's to the left of the arrow. And we break that bond apart. We separate them into the atoms itself, okay? But that is an endothermic process, and actually that reaction gets a little cold. With respect to forming the bond, which is basically the opposite of what we're going to talk about, it releases energy, okay? So we call that exothermic. And, you know, one way to remember, we got EX for exit the building, okay? Energy is exiting the system. So it gives off heat, and basically to the touch, it actually gets warm, okay? So energy is a product, and we put it to the right of the reaction arrow. And here is simply the opposite of what we just demonstrated, where you got the hydrogen atom coming in together with the chlorine atom to form the HCl, okay? And heat is given off, okay? Another analogy to this that you may have used in your real life is hot packs and cold packs that you could buy at the pharmacy. You go in there and buy a cold pack. In both cases, you take the pack and you smack it. The chemicals inside go in solution, reaction process, reaction proceeds. And depending if it's a hot pack or a cold pack, it's either going to get cold or it's going to get hot, okay? And the cold pack obviously gets cold, and that is an endothermic process. Whereas the hot pack obviously gets hot, okay? And that would be an example of an exothermic process, okay? So forming a bond, heat is given off. Breaking a bond, heat is required, okay? Heat/energy. So here's some more true or false questions. Electrons are shared in H2S, okay? So how do we answer that question? Well, we look at the hydrogen, we look at sulfur, and you know, they're both nonmetals. So therefore, they're covalent bonds. Therefore, they share, okay? Covalent bonds share electrons. So this would be a true statement. Okay. The bond between hydrogen and sulfur is ionic. What do you guys think? Do you think the bond between hydrogen and sulfur is ionic in this particular compound? That's correct. No, because hydrogen and sulfur are nonmetals, and therefore they're covalent. So that would be a false statement. And then the HS bond length is less than the sum of the two atomic radii. And again, that would be a true statement, right? Because individually, hydrogen and the sulfur have their own individual radius, but when they combine to form H2S, the radius, the electrons are shared, and there's overlap because they're sharing these electrons, and therefore the radius between the hydrogen and sulfur when they're bonded covalently is much less than the sum of the individual radius of the atoms, okay? Breaking the HS bond releases energy, and that is the false statement, okay? Breaking the bond requires energy. Endothermic. All right, so let's talk about Lewis dot structures. Now, Lewis dot structures are nothing more. In fact, I did an example earlier where I showed you hydrogen with 1 dot, and then I did the chloride with 7 dots, okay? Lewis dot structures are nothing more than looking at the A elements, determining what number of valence electrons they have, and then putting dots around that element to designate the number of electrons that they have. Okay, valence electrons. We don't care about the core electron, just the outermost shell. All right. The group, as you know, hopefully by now, will tell you how many valence electrons they have. Okay. And so you simply count the valence electrons, and what you do is you treat the element as a quadrant. All right. So let's say we got the element A here. Think of it as a box. Okay. And as we put, and now in this box, we only put a total of 8 dots around the element. So eventually, A will have 2 dots. If it's a noble gas, it will have a total of 2 dots per side of that box. It's a total of 8 electrons. Okay. Now, when we fill it, where you start makes no difference. What side of the box you want to do. And so you start, start right here. I got 1. And if it has 2 electrons, we go to the next side of the box. If it has 3 electrons, you go to the third side of the box. If it has 4 electrons, we go to the last side of the box. And now we have 5 electrons. We continue around the horn, so to speak. We fill it up, and now we can go. We got 2 electrons max per side, and we just bring it around the horn, so to speak, until all sides are full. We don't want to put, in other words, it would be incorrect to put, if they had 2 electrons, to put them on the same side, because we fill them up orbital-wise, the S electrons and then up to the P. But so keep them separated and only double up when you go around the quadrant. So I mean quadrant, think of it as quadrant 1 up here, 1, 2, 3, and 4. Treat it as a box and an invisible line there, and just go around the horn, filling it up with the number of valence electrons. Now, we need to understand the valence electrons and understand where we can get that information. Why do we need to do that? Because we're going to take that information when we start writing formulas for those compounds. We're going to determine from the valence electrons that every atom brings to the structure. Okay, let me repeat. From the total number of valence electrons that every atom brings to the structure, we're going to create a structure and a geometry. Okay, so we need to know how many valence electrons every atom brings to the table. Okay, and again, we're only talking about the valence electrons in the A metals, the A transition metals. All right, so if we do the Lewis dot structures for potassium, oxygen, silicon, magnesium, and iodine, we simply just have to find them on the periodic table and what group it is. Potassium is in group 1, so we write the formula for potassium and we stick a dot. Which side of the block, of that imaginary block, it's totally up to you. It doesn't make a difference. You go clockwise, counterclockwise to fill them, makes no difference, okay? You fill them up whichever way you want to fill them up. If we look at oxygen, okay, notice that oxygen is in group 6. And then, so we go around the horn, fill them up with 6 electrons. Notice there's 2 of them that are not together, because we fill either clockwise or counterclockwise each side of that imaginary box before we double up. And then silicon is in group 4. There's 4 valence electrons. And the same would be true for carbon, and that was carbon. Why? Because carbon is in the same group as silicon. Okay? Carbon would have, if this were carbon will have the same Lewis dot structure because they share the same group. Sodium would be the same as potassium, just like that. Okay? So on and so forth. All right. All right. So make sure you understand where to get that information. That is the valence shell electrons for those elements, okay? Because we're going to utilize it to determine the Lewis dot structures. Now, if you've not done so, which I hope you have by now, is download the shapes table. Okay, this is the shapes table. Notice the generic formula, A, B, and E, okay? The first column is the generic formula. The second column is the geometry. That gives you kind of attempts to give you a three-dimensional picture of the geometry of that chemical, that compound with that generic formula, okay? And I mean generic because there's a lot of compounds that have an AB generic formula. There's a lot of compounds that have the AB subscript 2, okay? And AB subscript 3, etc. So that's what we call a generic formula. I'll get more in detail. But all those compounds that share that generic formula will share the geometry, and that geometry has a specific name at the third column, which it will be either linear, trigonoplanar, tetrahedral, bent, etc. And then we'll give you, on the last table, we'll give you the bond angle. And that is the bond angle of the whatever is attached to the central atom relative to each other. Okay, so for example, when we look at this, obviously right here for AB2, this guy right here is a central atom. So is this one. And everything else, whatever it may be, is bonded to the central atom. So when we talk about the bond angle, we're looking at the bond angle of whatever's bonded to the central atom relative to the other element. So this could be A, and this could be B, and the bond angle between A and B is 180 degrees in this geometry that's called linear, okay? Now, the most common geometry that's out in nature is this one called tetrahedral. It has the general formula of AB4, where the central atom is A, and whatever's bonded to the central atom is designated with a generic formula of B, okay? And so this is an attempt to give you a three-dimensional picture. If I can draw it a little bit better, is say, if I got this one here, these two hydrogens will be in the plane of the paper here, if you will. Now I could draw a wedge coming out with hydrogen. That would be an attempt to demonstrate that this bond and the wedge is coming out of the plane of the screen, okay? And then if I make a hash mark to the back of the screen is another H. So that's an attempt here to show you three-dimensionally in a two-dimensional world what that geometry would look like. And that tetrahedral geometry is pretty common out there. The bond angle between whatever is bonded to the central atom is again 109.5 degrees. That is the most common geometry out there. I mean, bond angle, I should say. And whenever we change these species up here with hydrogen with something else, things happen. That bond angle starts to, especially if we start putting lone pair of electrons, they occupy a lot of space, and that bond angle starts to squeeze down. As you can notice here, we have a variety of different bond angles. Notice if we look at AB3 versus ABE. Well, let me stop for a second. A represents the central atom, whatever it would be, okay? B, always going to have one. A is always going to be one. BX, B represents whatever's bonded to the central atom. Okay, so X could be from 1 to 4. Depends on, you know, what the compound is. And then E, subscript X, E is any lone pairs on the central atom. Lone pair of electrons, two little dots. We have examples where there are lone pair on the central atom. X could be in a number from 1 to 2, and BX could be a number from 1 to 4, okay, in general, it depends on the compound. So if you look at AB4, there's no E, which means that there's no lone pair in the central atom. But if we look at AB2E, there is a lone pair on the central atom. Here's the B, here's the B, and here's the E. E is up here, lone pair on the central atom. Because that lone pair takes up space, a lot more space, it crunches that bond angle between the two B's. Therefore, that bond angle that was anticipated to be like this one up here actually gets squished, and it becomes less than 120 degrees. And that's because those lone pair have a big effect on the structure of the compound, and having an effect on the structure, having an effect on the properties. Okay. All right, let's go back. So how do we write the Lewis dot structures? Well, the first thing we do is we tally up the number of valence electrons that are involved in the structure that we are given. Okay, so we'll be given the central atom. We'll be told what the central atom is. It's going to be either underscored or will be in bold. And that means whatever follows is bonded to the central atom. Okay, so we can very quickly write the central atom, and then very quickly put around the central atom whatever follows and draw one line. Okay, that one line accounts for that bond between the central atom and whatever is attached to it. Okay, now going back to number one, we add up the total number of valence electrons from all the elements that come to the compound. If we end up with 10, then that is the number you work with. You cannot not magically, get rid of 2 or 1, or magically pull from the air any number because you came up short. Okay, you will. If you added up the correct number of valence electrons, those are the ones you make work with what you have. Okay, so you can't add or subtract spontaneously. You just got an X number of valence electrons. All right, now once we start making bonds, then you check to make sure the octet is fulfilled around the elements, like I was explaining earlier and giving you some examples. Okay, keeping in mind that hydrogen, all hydrogen wants is 2 electrons around it. That's it, period. Those 2 electrons are being shared. Now we're working with covalent compounds. We're talking about electrons that are being shared. Okay, now we check that the octet is fulfilled. Okay, then we double check with the number of valence electrons we calculated in number 1, and we're going to make sure we still had at the end that same number, because it can happen occasionally as you're busy making bonds everywhere. You might slip one, you lose a bond or a pair, or you may inadvertently add a pair by accident. Okay, so all through the process, keep an inventory of your electrons that you calculated in number 1. Okay, once you are done, but before you're done, this should really be the next step, rather than this should be step number 5, and this should be step number 6. So step number 5, after you've done 4, if the atoms in question that you have, if there are not 8 electrons around it, you can take a pair of electrons from the neighboring atom, if it has one, and create double bonds or up to a triple bond as needed until such time that the octet is fulfilled. Okay, now you're not creating more number 1s here. You are taking the valence electrons that you have, and if you got a pair on the atom all by itself, all you're doing is borrowing from Peter to share with Paul, so to speak, okay, to create a new shared pair. So it's still there, you just now shared it with another atom. And you continue doing that and checking to make sure the valence rule is fulfilled, okay? Then at the end, you identify from the central atom how many are bonded pair and how many are lone pair. Okay, lone pair are those electrons that are on the central atom, but are not shared with anybody else. From that information, you create the general formula ABE. Okay, all right, so A is a central atom, always a central atom. So that's always going to be there. Okay, B is whatever is bonded to central atom. A lot of times B could be the same element, and a lot of times they could be different. Makes no difference. Whatever is bonded to the central atom, you make note of how many. And then E is the number of lone pair, the lone pair in the central atom. All right, so let's do a formula. We're going to do it here, but I'll show you how we get to this formula. But we finally end up with water here, okay? And so we see we got A. Okay, we got A, because A is always the central atom, in this case is oxygen. Okay? B is subscript 2 because there are two hydrogens right here and right here bonded to the central atom. And in this case, we have lone pair on the central atom. Specifically, we have two lone pair, okay, on the central atom, which is oxygen. So our general formula is AB2E2. What do we do with that information? We go to the shapes table and we look for AB2E2. And look at here, AB2E2. Okay, here's the two lone pair. This was oxygen, these were hydrogens. Okay, its geometry for water would be called bent, and that bond angle is much less than 109.5. Why? Because those lone pair take up a lot of space, so that bond angle really gets pushed in. Okay. All right. All right, let's try one real quick, and we'll probably have enough time to do one, and then we'll call it quits here. All right, so we go, we are given the formula H2O. Now here, oxygen is the central atom. This is an example where normally I stated that 99% of the time the central atom is written first. Well, like I said, that 0.1%, you have an example here of water, where hydrogens are not the central atom, but by default and by convention is written, the formula is always written as H2O. Technically, it should be OH2, okay, with oxygen being the central atom, but you won't see it written that way. You'll see it written as H2O, okay? All right, so we look up hydrogen. This is hydrogen here. Hydrogen's group 1, okay? So it brings one valence electron, and there are two of them, so there's 2 times 1. Then we look up oxygen. Oxygen is in group 6, so it brings to the table 6 valence electrons. So we have a total of 8. Now, this number that you add up at the end should always be divisible by 2. Now, what I do, I divide that number by 2, so that tells me I got 4 pair to work with, okay? Now, for this small amount, 4 pair, you know, it's not a hard thing to do as far as keeping track of 8 dots, but you can end up with, you know, 32 dots, 32 valence electrons. It's a lot easier just to divide by 2 and just work with a pair, which means that I can just simply draw lines and that represents a pair, rather than having to draw 2 dots all the time. Okay, if you're not careful, you can end up losing your dots. All right, so we have 8 valence electrons to work with. This is the number right here that you have to work with, okay? You can't add to it, you cannot subtract from it. You gotta make 8 work because you have 2 hydrogens and 1 oxygen, okay? So we're working with that. Now, you're told that oxygen is the central atom. So I can very quickly write oxygen down as a central atom, and then note from the formula, there's 2 hydrogens that I can quickly put and bond to the central atom. Okay, just draw a line. And guess what? That took care of 2 pair. So I got 2 paired left. Okay, I started with 4 pair. I subtract 2 pair because I just drew the formula, and I got 2 pair to work with. I got to put them someplace, that 2 pair. Obviously, I cannot put them on hydrogen. Why? Because hydrogen follows the duet rule. Hydrogen is happy. It's done. Its outermost shell is full now with 1 pair of electrons around it. So the only logical place to put the last 2 pair have to be on the central atom. Because right now, oxygen only has 4 valence electrons. So it doesn't have the magical 8 number. So taking that 2 pair and putting them on the oxygen, that's 2 lines. Okay, now I got 0 pair. I've accounted for all my pair. I go back to the formula that I just wrote, and I double check to make sure I still have 4 pair or 8 electrons. I got 2, 4, 6, and 8. I've not violated my 8 valence electrons. I'm good to go. Okay, so that is the formula that I have. Now I create the general formula. A is my central atom, as I did earlier. B is a subscript 2, B subscript 2, because there's 2 hydrogens, and there are 2 pair of lone pair on the central atom. E can be confusing sometimes. E only is lone pair on the central atom. We don't care about lone pair on any other atom, only on the central atom. So that, ladies and gentlemen, is my general formula, which then I take to the shapes table and I determine the geometry from the general formula. Okay? All right. So moving along, I think we're doing okay. We should be done with this chapter for sure on Thursday. All right. Any let me stop it here. So slide in.